Okay, let's start the lecture today. So today we'll continue talking about multi-agent reinforcement learning. So in the last lecture, we talked about the formulation called the Markov game. And then we talk about how we're going to solve this game by using the Bellman-Optimatic equation. The Bellman-Optimatic equation is essentially very similar to the MDP version, with just the maximization replaced by the min-max. And this is like a multi-agent, like two-agent version. So this is basically the formulation and the planning. Today we will continue talking about the learning algorithms. Okay. So although we start from the reinforcement learning approach, we talk about the Bellman-Optimatic equation first, and then we say we can do planning based on Bellman-Optimatic equation. It turns out for multi-agent reinforcement learning, a lot of the early algorithm was not designed based on this Bellman-Optimatic equation. It was designed from another principle. So we will talk about the previous approach first. Okay. Probably I should not say classical approach, but let's say best response based approach. Okay. So for this style approach of algorithm, the key observation is the following. That given a fixed opponent, computing best response, we call it BR for short for this lecture, is actually somehow a single agent problem. We'll put a quote on the single agent because later we will see actually this single agent is slightly different from the single agent reinforcement learning we have been talking about. So basically, as we said, the major difficulty of multi-agent reinforcement learning is we cannot treat opponent as a fixed environment. While for this best response approach is kind of saying when I fix my opponent, then my opponent I can treat it as a part of the environment. So basically, then if we just computing the best response of the opponent, it becomes a single agent problem. So for this type of approach, we have two components essentially. So the first one is Nash finding algorithm. For normal form game. With best response oracle. That is, we will essentially one part is we just have algorithms which for normal form game that is a Markov game without any states and transition. as long as this algorithm is kind of like only access to best response, this algorithm design is basically reduced to computing a sequence of best response. We will see what kind of algorithm of this class later. But as long as we have this algorithm, then we can essentially just using this best response. And we know for like the multi-agent reinforcement learning, the best response, one heuristic is that we can just use a single agent reinforcement learning algorithm. Use single agent reinforcement algorithm to compute the best response. This has a lot of algorithm like VI, Q-learning, PPO, DQ, and a lot of things. Okay. So if we're using this generic recipe, that means the second part we kind of we have already talked about this for the most of this semester. So we only need to focus on the first part about the Nash finding algorithm for normal form game that calls best response oracle. We only need to focus on designing algorithm for this part so that we can solve this multi-agent problem. So this is actually has been the recipe for like solving StarCraft or a lot of the games before. And we will talk about what is specific algorithm, and later we'll talk about the drawbacks of this style of algorithms. Okay, so we will first talk about best response-based algorithms for normal form game. So since it's normal form game, it does not have states and transition, and so the algorithm is usually very easy to specify. So the first algorithm we'll look at is called self-play algorithm. It's a very simple heuristic for anyone who think about this problem. He might try to see whether this algorithm is good. So the algorithm looks like follows: for k equal to 1 to iteration capital K. We say pi 1, k plus 1, is equal to best response of pi 2k. Pi 2k plus 1 is equal to the best response of pi 1k, k plus 1. Okay. So those are the strategies. Mixed strategy, pi is like the mixed strategy. Pi 1 is the mixed strategy of the first player, and pi 2 is the mixed strategy of the second player. So basically, this is saying whatever, if I have pi 1k and pi 2k is the strategy of both players at a case iteration, what I will do is I will use the second player's case iteration strategy to compute the best response for the first player. And then for the first player, then I use the first player's strategy to compute best response, and we get the second player strategy. Okay. This is essentially I just have two players. One computes the best response of the other, and the other computes the best response of the first. Like we iterative doing this. This pi ik. Policy of the ice player. At the case app iteration. Okay. So what we can see about this algorithm, it turns out we can simply just try it on rock, paper, scissors. So what will happen is, for example, if we initialize with the second player to be a rock, then the first player will change to be a paper, and then the second player will change to be scissor, and then the first player will change to be a rock, and second player will change to be paper. So we kind of we end up within a loop. We're never able to converge to Nash equilibrium. So basically saying this is like a very bad algorithm. We should not try this algorithm because it doesn't even guarantee to converge to Nash. It can like stuck in some cycle. So after seeing this, you might wondering, okay, what if this is like saying I just look at the iterator. What if I kind of like average? Average means like because I stuck in this cycle with like a rock paper scissor rock paper scissor. If I do average, then somehow I end up with 1/3, 1/3, 1/3 probability on playing all the actions. So it turns out that average helps in this specific game, rock, paper, scissors, but it won't help in general. This is also very easy to see. For example, I can just slightly tune the reward for rock, paper, scissors. When rock, paper, scissors means like if rock, paper wins rock, we get a reward 1. Scissor wins paper, we got reward 1. But I can slightly tune it so that I'm saying like when paper wins rock, I got a reward 1.5. When scissor wins paper, we got a reward 2 or something. In that case, the Nash equilibrium will no longer be uniform distribution over action. It will be slightly favored over scissor because when scissor wins, it has like a higher utility than paper wins. But in that case, if we just do this best response plus averaging, we'll still end up with 1/3, 1/3, 1/3 probability. So this is not helpful in general. So in general, this cell play algorithm is not a good algorithm for doing best response. So how should we fix this algorithm? If this algorithm, like a naive algorithm, is no longer working? So it turns out there's a very famous algorithm that proposed as a variant of this algorithm called a fictitious play. So this algorithm is proposed by Brown, 1949. So the algorithm is similar to cell play, but it differs in slight details. Again, we have some iteration for k equal to 1 to k. So we'll do the similar updates. Pi 1 k plus 1 is equal to the best response. So the only difference is the best response is no longer the best response of the immediate policy, of the current policy of the opponent, but it's actually the average of all the previous policy of the opponent. So this is like a best response of 1 over k times pi 2 1 pi till pi 2k. That is, I look at the average, look at the policy of my opponent across different episodes. And I do an average, essentially I look at the average policy of my opponent and I find the best response for that. That is how we do the fictitious play. And by symmetry, we can also do the same thing for the other player. One over k plus 1, pi 1 1. Till pi 1 k plus 1. Okay, again, this notation pi k is the policy of ith player at the kth iteration. So only difference is I'm no longer finding the best response of the current policy, but I look at the best response of the average of the previous policy. So this is like computing the best response policy. To the average policy of opponent. And this makes a lot more sense in rock, paper, scissors. We can imagine like when we do this averaging thing, and eventually this averaging will converge to the Nash equilibrium. So we can actually prove this actually has theoretical guarantees. This is by Robinson, 1951. Basically, it says the policy of fictitious play converge to Nash equilibrium. So this is actually a very, very famous result back in like 1951. It's kind of like also surprising to a lot of people because this is in just such a simple dynamics eventually will guarantees you that will converge to Nash equilibrium. So this is also the reason even till nowadays there are still a lot of algorithms just leverage the fictitious play algorithm to compute a Nash equilibrium. But as we said, this is like the theoretical course, so we're not very happy with just stop at this asymptotic convergence. This says eventually it will converge to Nash equilibrium, but across this class, we will talk a lot about how fast we kind of converge to a Nash equilibrium and how many samples. In this case, it's really about how fast. Okay, so how fast? If it's use infinite amount of time, like k need to be like a super large, that won't be useful, right? So it turns out when we talk about how fast, it's actually very tricky. Even till nowadays, I don't think it's like a fully solved problem. So what we will know is actually the answer is not very good. So probably it's not fast at all. So what we know is first we can inspect the proof of Robinson, 1951, the original paper that proves this will eventually converge. So the convergence actually requires something like 1 over epsilon to the power of omega a, where a is number of actions. In the game, in normal form game. to find epsilon Nash. Where epsilon Nash, we kind of like already talked about in the last class. So by epsilon approximation to Nash equilibrium, we measure it by duality gap. So this is actually saying that if we just use the original proof, this is like terrible, because for any reasonable number of action, like for example 20, 30, this will be already like huge, and this convergence is like super slow. So there's some further research later that trying to improve this complexity. They kind of like believe maybe it's the artifact of analysis. Maybe the algorithm actually converges a lot faster. So there's a very famous conjecture by Carling. In 1959, that this rate can be improved to order of 1 over epsilon squared. Basically, it says probably this exponential in A is just some artifact, and in reality, this algorithm won't even need the action number, like exponential in a number of actions, to converge. So this is a conjecture, and like back in like 60 years ago. But then this just conjecture keep opening for very, very long time, and nobody is able to solve this conjecture. And there's some partial answer to it in 2014 by Daskalakis and Penn. The papers kind of like say claims it can refute the conjecture, basically saying this conjecture is not true. But the paper kind of like assumes we have some adversarial tie breaking. That is, whenever there's a tie, actually, they're able to do some adversarial way, that even inconsistent way. Like, for example, whenever there's a tie, this time I can choose that action, and next time I can choose this action in some adversarial fashion, which is not very common in practice. But basically, if we have this very weird, I won't say weird, but like a very strong adversarial tie breaking, then basically they can construct some counterexample to say to prove you actually require something exponential in A. This is unavoidable. Okay, so basically this is about the adversarial tie breaking for the if we have some consistent tie breaking, that every time for example, we do tie breaking in some like a dictionary order or some like fixed order, then it's actually unclear what is the rate. This is still an open problem right now. And in practice, if you run this algorithm for, like, test a bit of this fictitious algorithm, maybe it won't be like exponential in A, but there are some like high order polynomial in A. It's kind of like it's always observed in empirical. So it seems like this algorithm is indeed not very fast. So the next question is how we're going to make this algorithm faster if this algorithm is actually not that good. So there's a large class of algorithm, which we just talk about one representative one, that is called double oracle. So the whole idea is, for example, when we have a lot of, my opponent have a lot of policy that pi 2, 1 to pi 2k. And I also have a lot of policy that pi 1, 1 to pi 1k. I can essentially compute the relative performance between them. So, for example, we can say this is a value or like the utility of playing pi 1i, i's policy, against pi 2i. So we call such matrix MK. That is a utility matrix for if we kind of like use the like previous policy of one player against player policy of the other player, and we look at what is the performance. This is like k by k matrix. So double oracle is kind of like the algorithm look like this for k equal to 1 to capital K. I think the part of generalization is we see like in fictitious play, this is like average. This is a uniform average. And we think this is not very natural. And we want to have a smarter way of compute this weight. Okay. So what we will do is we will essentially select some P and Q in RK by some specific way. Okay. And then what we do is pi 1 k plus 1 is equal to best response of summation I from 1 to k pi pi 2i. And pi 2 k plus 1 is equal to the best response of summation I from 1 to k qi pi 1i. Okay, so this is just slightly generalize the fictitious play so that we're no longer just 1 over k ways, we're using some other ways, pi and qi, where p and q is computed in some more complex fashion. So there's one way to compute this p and q vector, and that is called double oracle. Double oracle kind of specify the specific way of computing is to choose this p and q to be the Nash equilibrium of MK. So MK is a k by k matrix. When you compute a Nash equilibrium, it's actually a mixed strategy for the first player and mixed strategy for other player. So it's kind of like a probability for P, probability for Q. So this is one specific strategy called double oracle, but in general, like they also proposed the algorithm called PSL, which called a policy space. Response oracle. The name sounds a bit counterintuitive, but if you look at the algorithm, basically they're just the generalization of a double oracle, but using some other ways to compute the meta strategy PQ. Okay. So essentially, We call PQ meta strategy because PQ is actually a probability over the existing strategy so far. So it turns out, if you look at the paper of Alpha Star, they essentially just like for StarCraft 2, they essentially just leverage some strategy of like in the class of PSR. They design some like league training, but it's more or less you have like this matrix and design some score based on this matrix to compute a meta strategy, and in the high level is performing this kind of updates. So what we can say about this double oracle algorithm, for example? So the proposition is essentially says the double oracle algorithm finds Nash equilibrium of a normal form game with A actions in order A iterations. So in the first class, this like proposition looks a lot better than the fictitious play one, because fictitious play says it requires something like exponential in A. Well, here it's just a linear in A. But it turns out this proposition is actually pretty straightforward. It's actually not saying much. Okay. So the whole reason is you can more or less prove that for double oracle, in every iteration, like first we can prove the pi ik is always a single action. This is basically because for normal form game, you can always use a pure strategy to achieve the best response. Best response can be always achieved in a single action. And then you can essentially also prove at every iteration the algorithm will add a new action or stop. Okay. So basically, if the best response you computed is not a new action, that means this matrix will not be updated. So whatever the policy you have here is actually the same. What you have is just exactly the same action with additional row. So in that case, when you compute Nash equilibrium, everything will be the same. So the algorithm essentially will not do any update, meaningful updates. So only if when you compute the best response, this is some new action, you will add a new action to this matrix, and you essentially expand this matrix. And then, if we kind of like always add a new action, didn't stop, and then MA will become a 4-game matrix in A iteration. This is just because the normal form game only have A actions. If we kind of keep adding a new action, then after A iterations, the MA matrix just becomes MK matrix becomes the original matrix. Okay, so that is when K is equal to A. This is just the original matrix. So that's why it's also not very surprising. Essentially, a lot of heavy work has been done in the double oracle. So basically, we have been talking about several algorithms that self-play we know it doesn't work, and fictitious play, it's a bit slow. So that's why basically saying in practice, what you should do is this double oracle or PSL algorithm, which you compute this matrix and you compute some new meta strategy, and do this best response based algorithm. So now we talk about, once we know the algorithms for normal form game, we talk about how when we combine this normal form game algorithm to single agent reinforcement learning algorithm, what might be the problem? For solving Markov game. We're saying the converted algorithm is actually very straightforward. All we kind of modify for this double oracle, for example, or PSL algorithm, is we replace this best response. Instead of finding the best response for normal form game, what we replace it is using a single agent reinforcement algorithm for solving this best response. For example, I will use PPO and the fixed opponent to be like this kind of policy, and I find the best response to be my current policy. So there are several caveats when doing this approach. The first is by doing so, we're essentially converting a Markov game to be a normal form game. Okay. We're saying in the high level, this is like a normal form game so that we can apply the double oracle or PSL. And the low level is like single agent reinforcement learning. So when we talk about the complexity for the normal form game, we always, one very important thing is the number of action. Number of action for the normal form game. So when we convert the Markov game into a normal form game, the number of action actually becomes the number of policies. In Markov game. So as we all know, for Markov game or MDP, one thing very complicated is this number of policy is like huge. So easily, if you just do some first, it's if you compute like a randomized policy, it's infinite. But you can also do some discretization or epsilon covering argument, and roughly number is like 1 over epsilon to the HSA, where H is horizon in the Markov game, S is number of states, A is number of action in Markov game. So this is why this conversion is actually not very efficient. So that means whatever you pay for OA or for exponential in A, you actually pay A by replacing A by this quantity. This is already exponential. So fictitious play in the worst case would be double exponential, and the double oracle in the worst case would also be exponential. So this is why this first thing is not very efficient. The second is finding a best response of a mixed strategy. Sorry, a mixture of policy. Is not it's actually not an easy single agent IO problem. Standard single agent IO, what I mean is like by the MDP. So what I mean there is we kind of claimed earlier that when we have a Markov game, n plus opponent is fixed opponent playing some Markov policy pi 1 or pi 2. Let's say pi 2 only depends on the current states, something like that. Okay. So in this case, this becomes an MDP in the player one's perspective. This is still true. This has no problem. But the problem part is when we do double oracle or PSR or even fictitious play, we're not finding the response of a single Markov policy. We're finding a best response of a mixture of policy. That is, we're considering actually the problem of a Markov game plus fixed opponent playing a mixture of pi 2 k dot s. Okay. So each individual policy is only depends on the current states, but there are multiple policies, and we're playing a mixture of them. So it turns out you can essentially see a mixture of Markov policy is actually not a Markov policy. That you cannot just represent this mixture by a single policy only depends on the current states. Okay. So this turnout is no longer a MDP in the player one's perspective. So this is the reason, in reality, if you want to say the principled way of designing an algorithm, you should not just use a single agent reinforcement learning algorithm to find the best response, because those algorithms, like we said, the V-learning, value iteration, Q-learning, and also like, for example, PPO, they are originally designed only for MDP. Well, this is like beyond MDP. And whatever algorithm we're using there is, if we use the MDP algorithm directly here, it's only a heuristic. It's not principal. It's not guaranteed to find the best response. OK. So all those two kind of concludes that those line of algorithms that are designed based on the black box approach of single agent L plus best response oracle actually does not fully utilize the detailed structure of Markov games. I think these two are essentially the reason, although those are algorithms which are kind of people tried a lot in practice because it's something simple to think about. But on the other hand, in theory, in principle, you cannot actually prove any efficient guarantees for this line of algorithm so far. Like the best response plus single agent algorithm, just because all those problems we have mentioned before. So we kind of conclude the most important thing is in order to get principled algorithm for Markov game is we need to essentially better utilize the detailed structure of Markov game. So how are we going to do that? So we will actually use our old approach. We have been dealing with MDP so far, and our approach has been based on the dynamical programming to solve this. And now we're dealing with Markov games. So we will also develop our reinforcement approach or dynamic programming approach for solving this class of model. So this is IL, or dynamic programming approach. So we again talking about several settings. In the MDP, we talk about generative settings, exploration settings. So we look at the generative setting first. Essentially, this is a simulator setting, and we look at the tabular case for Markov game first. So remember, when we have the generative model, what we can do is we can uniformly sample SAB. That is, because we have a simulator that takes in the states and action of a different player, and we get reward and S prime, and we can use this to estimate the empirical transition matrix P hat. P hat is a transition to S prime from SAB. Once we have the empirical transition, we can essentially run the value iteration. Well, here it's a multiplayer game, so what we run is called a Nash value iteration. But Nash value iteration is essentially the same as an original value iteration with just a very little modification. So So just remember, when we do the value iteration, essentially we're just running a Bellman-Optimality equation with the transition replaced by this empirical estimate. So what are we going to do here is, again, run Nash value iterations by doing this Bellman-Optimality equation. That is, we have the update QH SAB is equal to RH SAB plus we use empirical transition to do VH plus 1 SAB. Okay. So this step is basically the same, and we will do for H from the last step to first step. So the only different steps is the V-value updates. Where originally, we're just maximization over Q, because that's a single agent problem, and a single agent just want to maximize the value. Well, now it's a multiplayer game, so one player just want to maximize, the other player just want to minimize. So instead of just maximization, we will do a min-max in this case. So we're maximization over mu h, and minimum over nu h, summation AB, mu h A S, QH SAB, and nu h BS. Okay. This is essentially the same as the last time we do the Bellman-Optimality equation. We replace the max by minimax, and we always do the randomized policy. And you can also think this is basically just compute a Nash value for the matrix normal form game, which indexed by the current states. So kind of like this, for this Q value, if we fix the states, this Q value kind of like denotes a normal form game with utility QAB for like first player play action A, second player play action B. And this is just computing Nash value for this Q value at a state as S. Okay. So this is essentially the algorithm for Nash value iteration. And we can essentially do similar analysis to VI in generator model. To show sample complexity of Nash VI. I think it's a very good practice to use to use existing knowledge, especially to recap what has happened in the value iteration on the generator model we learned before, and how to adapt it to like this game scenario. So this is basically what happens for the generator model. We'll talk a little bit more for the exploration setting, because that's slightly different. So in the exploration setting, where we will, I think the whole idea is we have a Nash value iteration, and the classical way is we just combine Nash value iteration with optimism. So this gives the algorithm that's called optimistic Nash VI. It's also by some paper in my group. in 2020. So remember, the value iteration, optimistic value iteration, composed two parts. The first part is we compute the Q value, and then second part is like executing a policy. So we'll do the similar thing here. K equal to 1 to capital K, and for H equal to capital H to 1. For all state action pair, we compute the optimistic Q value. That is Q upper bar is equal to RH SAB plus expectation P at H VH plus 1 upper bar SAB plus some bonus. So the tricky part is we have the optimism because in the single agent setting, we only care about the maximizing the reward. But here, because we have two players, one player trying to maximize, the other player is trying to minimize, it turns out having just upper bound is not sufficient. So we also need to have a lower bound, which a lower bound will serve as an optimism for the minimum player. So what we will do is, again, we'll have another optimism, which is optimism for the mean player, that Q lower bar is serve as a lower bound. We will do the same update that RH SAB plus P hat H plus 1 bar SAB subtract beta. So the only difference is that we subtract the bonus. Here we add the bonus. So this step is relatively straightforward. We just have a Q value. And the tricky part now becomes the V value part. So we'll write a naive algorithm first. So what we will have here is instead of having a one Q value, we can compute a Nash equilibrium. Now we have both Q upper bar and Q lower bar. We have two Q values that serve as an upper bound and lower bound. So this becomes a lot trickier because the Nash equilibrium now is no longer a single game. It's kind of seems like we have a two utility matrix. So one naive idea is what we can do is we can compute this by mu HS, nu HS, to be the Nash equilibrium of Q upper bar HS. This is a Q lower bar HS. Okay. Just remember, this is no longer the standard Nash equilibrium. This is no longer the zero-sum game. This is a Nash of a general-sum game. Okay, because essentially, we're no longer saying the utility of the first player is the second player. So we'll just use Q upper bar as a utility for the max player. And this is a utility for the mean player. So now those two players actually are the loss of the mean player. So actually, the two player has a different utility and a loss. They no longer sum to 1. This is like a general sum. And in general sum, we will still able to find Nash, but we'll talk about the caveat of this problem later. But in short, this subroutine can no longer be computed efficiently. This is actually a PPAD problem, PPAD hard problem. So we will talk later how to fix it. But a simple algorithm is first we compute the Nash equilibrium of a general sum game. General sum in a sense, the first player uses utility Q upper bar, and the second player uses utility of Q lower bar. And then we compute the upper bounds on the V value by just essentially doing summation of A and B, mu h, Q upper bar, SAB, and nu h, B given S. Essentially integrate this Q upper bar by mu and nu, and similarly for the lower bound is also the same. A given S, Q lower bar, SAB, nu B given S. Okay, so we just compute the Nash equilibrium policy, and when we kind of directly do an expectation over Q upper bar and Q lower bar, and this gives the V value. And then all we need to do is we will execute policy mu and nu collect sample, collect one trajectories, and then update the transition p hat. Okay. This is the same part as standard value iteration. So we kind of like see this part is basically we just have an upper bound and a lower bound with one adding the bonus and one subtract the bonus. And because we have a 2Q value, now we need to compute a Nash equilibrium of a general sum game. And once we have the Nash equilibrium, we just use this as a policy for Q value, and we do everything. So it turns out by doing this vanilla algorithm, there's one very important problem. That is computing Nash equilibrium for general sum game. Basically anything beyond zero sum game. For zero sum game, Nash equilibrium is still fast to compute, but for general sum game, is so-called PPAD hard, PPAD complete. Basically, this is a complexity in the computational complexity theory, but it essentially says it's something rather difficult to solve, and there are like a lot of complexity hierarchy. But one thing we are very sure about this PPAD complete is so far, we don't know any polynomial algorithm that is able to solve any problem in this PPAD complete class. So basically, no polynomial algorithm so far. In the worst case. This kind of is bad because although like we say in the function approximation, a lot of algorithm we design is statistically efficient, but in an earlier lecture, for every algorithm we develop for the tabular setting, everything is computationally efficient, like we can solve it very fast. But here it seems like for Markov game, even for the tabular, for the tabular case, we somehow ran into some computational difficult issue. So it turns out this is actually not the problem is hard. It's actually this algorithm is not well designed. We can actually better design this algorithm to better solve the problem so that we can solve it in polynomial time. So the trick is we can replace the Nash finding part by another subroutine called CCE. Okay. So we replace this part. So-called CCE. I'll first write out the algorithm and then explain what it is. So the algorithm will now becomes just simply we will find a policy that is actually not necessarily a product. So when we write this mu and nil, that assumes like the sample of action A and sample of action B is kind of like independent. So this is like product policy. But now we might have some correlated policy. That is the sampling of A and B may no longer be independent. So we will compute this pi to be the CCE of Q upper bound and Q lower bound. And then we will do V updates, V upper bar. It's just the summation of A and B, pi AB given S, Q upper bar, H SAB. And similarly, we have a lower bound, also the same. So this doesn't say much because we kind of like this CCE is still a black box. So we need to talk more about what is this CCE subroutine. So CCE, in general, we can look at this subroutine essentially takes two matrices, one matrix Q upper bar that for fixed S, and the other matrix Q lower bar for fixed S. So for example, if we compute the Q upper bar and Q lower bar, it returns so-called coarse correlated equilibrium. Which is a joint distribution. Pi in this simplex of A cross B. That is in the joint action space A and B, and this is like joint distribution over this joint action space. So this kind of it's very different from Nash equilibrium, which is a product policy that the distribution of A and distribution B are like independent. Well, here they allow some correlation that essentially allows some collaboration between them. So by its name, you can see this is like some sort of equilibrium. But what is the definition of such equilibrium? So it basically says when we find CCE Q upper bar and lower bar, the pi policy pi needs to satisfy the following equation. And its expectation, if A, B both sample from pi, Q upper bar, A, B, that is if both players act according to the policy pi, acting according to equilibrium, this will be greater or equal to max A star expectation of AB sample from pi, Q upper bar, A star B. This is basically saying if the utility the first player get, if they both of them perform according policy pi, is actually greater than if my opponent still play according to pi, but I kind of switch to something uncorrelated to this. Okay, I no longer collaborate with them, and I just pick some fixed action A, and I won't gain anything. Okay, so this means I don't have any incentive to change to some fixed action. Similarly, we also have the other part that is less or equal to the minimum of B star expectation of AB sample from pi, Q lower bar AB, B star. So the intuitive interpretation of CCE is like an agent won't gain anything. Like if we already reached the CCE, then an agent won't gain anything. By between the shared protocol, essentially we're saying we will sample from some coordinated policy. But now if I betrayed, I will just do some fixed A star. I can no longer see how my opponent is sampled from policy pi. And so by betraying, and then the other agents no longer collaborate or coordinate. By no longer collaborate in the sense, like originally, if we need to sample some joint action from pi, essentially we have like a shared coin toss. We toss the coin, and everybody, both players will be able to see the coin toss, and then we sample from according to this distribution. And now when I betray, I'm no longer able to see the coin toss. So my opponent is just according to some hidden, doing some random strategy according to some hidden coin toss. I can no longer see the coin toss, so I won't be able to gain anything. And there's a stronger version if I'm able to see the coin toss, and that's called correlated equilibrium instead of coarse correlated without the coarse more modified. But here it's okay, we just can talk about the CCE. So we'll talk about a brief reason why we can replace the Nash finding by CCE. First, we note for general sum, we know CCE is basically just having some linear constraints. So CCE is actually computed by linear programming. We know for linear programming there are a lot of efficient solvers, so this is a polynomial. Well, Nash is PPAD hard. We kind of already mentioned that. Complete. The other thing, there are several properties regarding to Nash and CCE. We can actually show that first, Nash equilibrium equilibrium is a subset of CCE. So you can essentially see the Nash equilibrium actually satisfy a stronger condition than CCE. So whatever is Nash equilibrium is always a CCE. But on the other hand, if some policy is a CCE, it's not guaranteed to be Nash equilibrium. So then if it's just superset, then that means finding CCE may be very different from finding Nash. So what we will have next property is very critical in this case. That is, if I find some policy of CCE of Q and Q, that is a CCE of a zero-sum game. So both utility are the same. Then and in general, this is like correlated policy. But we can let mu and nu to be the marginal distribution of pi. So that is, for zero-sum game, I find a correlated equilibrium, and then I just computed a marginalized distribution for the first player and second player. You can actually prove that mu and nu is a Nash for Q. So this only holds for the zero-sum games. And this is the essential reason why we can actually replace the Nash by CCE here. Because we know this is an upper bound and this is a lower bound. Intuitively, you can think when we have enough samples, this Q upper bar and Q lower bar will eventually kind of like become very similar and become one value. Or even if it's not that one value, it's like very close. So in that case, we can essentially leverage this property so that we're guaranteed whatever the policy we find by marginalization is kind of close to Nash equilibrium. So we're running out of time. We will talk about the formal guarantees of this optimistic Nash value iteration in the next lecture.